Hello everyone. Thank you for joining in, and also hello to future viewers that might see this presentation. I'm Jovan, and now I'm going to tell you a little bit about the DataFrame library Vaex and how you can use it for building fast and responsive data apps. Small introduction: I work as a data scientist in a company called Tickets, and I'm joined today also by Maarten Breddels, who is the primary author of Vaex, and he will be lurking and monitoring the chat in Discord and on YouTube. So if you have any questions throughout this presentation, please feel free to write it there, and I think he'll do his best to answer it. So let's jump into it. What is Vaex? Vaex is a data frame library, a high-performing one in Python. When you think of a data frame library, most of you will immediately think of pandas, and with good reason. Pandas has been probably one of the main reasons why Python is the data science language today. However, we all know about the kind of limitations that Pandas has in terms of performance and working with larger data sets. And this is where Vaex comes in. So Vaex promises to work with a lot of large data sets on a single machine. And that's the goal of the project. The idea is to work with as large data sets as you can fit on a single hard drive and fairly interactively. So that means a single node processing like a machine, like your laptop or a single machine in the cloud should be able to work with around 1 billion points in a reasonable time of a couple of seconds per typical operation. The API is similar to Pandas, although Vaex itself does not build upon Pandas. It's unlike other projects, it doesn't want to extend or make it scale. It's a fully new implementation, but we're trying to keep close to the Pandas API as much as possible, hopefully to limit the learning curve. Of course, it's free and open source. You can easily try it and install it via pip and conda. So how does it work? How is it so fast? It's a combination of fast, efficient C++ algorithms, mainly developed by Maarten, and streaming data concepts. So Vaex is optimized for reading data from disk, and Vaex actually streams the data from disk and applies these efficient algorithms to do fast aggregations and processing. This is greatly helped by storing the data in a smart way. Usually this involves memory mappable column storage, like HDFI files or Apache Arrow that can be easily memory mapped. Of course, if you have Parquet or CSV files, that will work as well. In addition to this, we have what we call an expression system that, as you work with Vaex, behind the scene, it computes or creates a rather like a computing graph, which when executed allows for better computational efficiency and memory efficiency. Vaex is lazy, so it will only evaluate expressions when absolutely necessary. And last but not least, many operations can be additionally sped up by using just-in-time compilation. And the interesting thing here is that we also support GPUs. So it could be a bit of a gimmick at some point, but we do support both NVIDIA GPUs and GPUs on Apple machines. Under the hood, Vaex has two main components. So the core of Vaex is written in C++, as I said earlier, various efficient algorithms, mainly developed by Maarten, that do the core operations such as group by, statistics, computations of various types, or computing hash maps for doing joins and so on. However, we also rely on the Apache Arrow project for additional functionality. And on my screen, you can see some examples. This is by no means an exhaustive list, but just to give you a sense of where things are coming from. We also try to contribute to the Apache project whenever possible. Like in the past, the string operations that are now part of the Arrow project were developed by Maarten for the purpose of Vaex, and then we worked together, and now they're part of the Apache Arrow project. So this is a little intro of how things work. I'm going to demo this in a second, but just to give you a sense of how things work in Vaex, which is a bit different to Pandas, a bit of a paradigm shift. So when we work with a file, let's say we want to open it, and the file is stored in a friendly HDFI file format. What happens is that Vaex says, okay, I'm going to do nothing, but I know what the metadata looks like. And by that, I mean, I know that this file has 2 columns, and I know where they're on disk because I can memory map it. Now, let's say I want to create a second data frame that is just a filter of the first one. What happens is that the data is not being copied, and it's actually immutable, and it keeps on living in the disk. and nothing has happened in the data, but now we have this dictionary, essentially a dictionary we call a state, that embeds all the operations we've done to reach this data frame 2. So in this case, we want to filter data frame 1. The data hasn't changed, but we say, okay, whenever we need to work with data frame 2, we need to execute this condition, this filter. And the same thing happens when we want to add a new column. Let's say we want to add a new column Z. We still unchanged. We don't change anything to do with the original data. We don't create a new data in memory, but we add an additional field to our main dictionary that says, okay, now there is such a column called Z that exists, and to do it, to work with it, you need to evaluate this expression, and this is done on the fly. This enables all kinds of cool applications, most notably in the field of machine learning, where as a byproduct of this workflow, one can get automatic pipelines of basically any kind of pre-processing or building ML models. But this is perhaps a talk for another day. And today, I'm going to focus on the various performance optimizations you can do with Vaex, mainly as a backend for a data app. So what does a modern data app need? In fact, today data is always kind of growing. Sometimes that's good, sometimes it's annoying, but we need to be ready for it. Of course, we want our data app to be fast and responsive, regardless of how big the data size is. With data apps, the operations are often repetitive. We tend to start on the same homepage, and maybe the first few clicks are kind of the same. And we do want to have the flexibility of computing various statistics, custom visualizations, and maybe even interface to various ML models, something that many off-the-shelf BI tools cannot always do. And Vaex can help here, mainly because of its high performance, the C++ and Pyro backends that we talked about, and many of these additional steps that I'm going to demo to you in a second that really help in creating data apps. So bear with me. Let me go to a Jupyter notebook. I hope you can see this and that it's the right amount of font size. Perhaps I can increase it if necessary. So for this demo, I'm going to use a portion of the GDAL dataset. Just to introduce it very quickly, the GDAL is a project that scans and monitors the world for any published article and basically creates metadata about the published articles. It's a very fascinating project. I recommend you check it out. Also, the dataset is very fun to work with, especially for testing sort of big data tools. So let's go into it. Let's import the usual libraries. And our snapshot of this data set that I have locally on disk is around 350 gigabytes. So it's kind of large enough to be considered a problem under normal circumstances. But working with this file with Vaex is quite simple. You see, opening is almost immediate because we don't really touch the data. Vaex just knows where the relevant columns are on disk and gets to read some metadata about it, like the number of rows and number of columns. We can inspect the file, and this is also quite fast. We can do it multiple times because we're not really reading the entire data set, but this is essentially a hidden tail operation. And because the data is memory mapped, we can immediately access the top and the bottom 5 rows. So we can easily inspect this file. If we want to filter or make copies, it's essentially the same procedure. So let's say we care only about a subset of the columns in this file. Again, we don't really make a copy. Vaex just accesses the rows that it needs and the columns that it needs in this case. Accessing a single column is just as easy. We get a simple preview of the top and bottom 5 rows, and it doesn't really matter how big this number is, how many rows you have. You always access the first and last 5 rows. It will always be fast. So in this case, for this dataset, this average tone is something like a sentiment of the article, because the GDAL data reads it and processes and gets let us know what is most important about an article. And we have another column, actor type, where actors in this dataset are something like entities that are related to the article. And these have various codes. So going back to Vaex, we can do various operations. So for example, if we have a division between two numerical columns. Again, we don't have to stream over the entire data set. In this case, we just get a preview of what would happen if we do it, the first and the last rows. It's very fast. We can then take this expression and assign it to a data frame. And then this expression, like I showed in the intro before, will be acting as a normal column, just the same as the other ones, even though it's not doesn't live in memory, but this data frame knows that it exists, and when it's asked for it, it will be evaluated on the fly. That makes that saves a lot of memory, and especially in machine learning procedure when you have to create a lot of features. Where things do get eagerly executed is when you need to compute aggregations, or you need to fundamentally change the structure or nature of the data frame, such as computing a mean. So now, instead of just doing a preview, Vaex will actually compute the mean, and you see that it's for like 600 million rows. It's quite fast. It's less than a second. And this is where Vaex excels, computing all kinds of statistics in numerical columns. For example, we can do a count of a column. We can compute the mean. Now we're computing the mean over two columns in the same pass of the data. That's a nice optimization. We can also do this statistics like count and mean and so on along an axis, and being along an axis, which essentially gives us a histogram. And yeah, this is maybe not so pretty, but you get the idea. And Vaex also offers a wrapper, so you can get a nice convenience method that you get a nice histogram function. But basically, this is what we're doing. It's not just about numerical values. We can also do the usual type of aggregations, and the value counts method is probably my favorite method in data science, no matter which data frame library I'm using. So in Vaex has a bit of a special treatment, some extra optimization behind the scene to make it faster. And the usual, for example, working with n unique values and group by. And you see, we started with a 300 gigabyte data file. We're doing all these kind of operations on a single machine. You kind of forget that you're working with sort of large data or kind of sort of big data, but everything is kind of smooth. And here, just I want to take a second to mention another one of my favorite features of Vaex. So this is a standard group by operation. We're grouping by two columns, and we're computing the mean and the standard deviation of this one column, very similar to the pandas notation. However, here I do something more special. For example, I do want to calculate the mean of this particular column, but according to some additional filter. And in Vaex, we can do this by passing the dedicated aggregation function. I can specify what aggregation I want to do, but also if I want that aggregation to obey a certain condition. And this is quite convenient. You can imagine how would you do this in SQL or other data from libraries. You probably have to do two group bys and enjoy them. It's a bit more cumbersome. So in Vaex, we do care about speed, but also about convenience. So that's a very quick and hopefully not too dirty introduction to the main features of Vaex. And now let's apply them to create a nice, hopefully fast application. So here are some definitions of the actor codes of in this GDAL dataset. I took this from their documentation. Do check it out. It's really, really fascinating dataset. And I proceed to create a simple filter function that will take in a list of codes, and it will basically filter out every other entry that doesn't have that code. So the syntax here is exactly the same as in pandas. However, do know that we are doing 6 filtering operations here over this big data set, and optionally maybe additional 2 operations if a user specifies like a limit on the year. This is all calculated lazy. We don't need to use it yet, so you get to see a preview immediately. So let's filter our data frame with the filter that we specified above. This is still lazy. Nothing has happened. And at this point, we want to start like maybe optimizing our process a little bit. So the first thing, let's say we want to compute a series of operations. It doesn't really matter what they are. You can look at them in your own time later. But essentially, we're doing things like we're counting, we're computing some mean, some average of columns, some group by, and so on. So some things will be fast and some things will be slow. By wrapping this whole workflow in a context manager in Vaex with this progress tree context manager, and I execute this operation, you get to see a tree of timings. So you can really drill down into what makes your process or application slow or fast. So for example, in this line over here, we're calculating the mean of these two columns. Here we can see that, yeah, we're calculating the mean, but to calculate the mean of this column, we need to calculate the sum of it and also count how many items are in it. So we get to see exact timings of each operation. So then we can really drill down into whatever process we're doing that maybe is slow, maybe there is a way to improve it, or maybe replace it with some more efficient process. And not only that, next to the timings here in square brackets, we do get to see numbers. And these numbers indicate how many times over the course of this progress tree, Vaex had to read data from disk from scratch. So how many passes over the data it had to go. So in this case, for example, to calculate the count at the start, this is one pass of the data. Then to calculate the means of these columns, it's another pass of the data. Then to calculate the sum, it's a third pass, and so on. So this also gives you an additional insight about the performance of your application or your pipeline or transformation, whatever you may be working on. And yeah, this is a summary of what we calculated at the end. So you may be asking like, wow, this it's quite fast, but you do have to read the data from this quite a lot. Can we do better? Like, yeah, sure, we can do better. And that's the next topic, delayed computations. And this is maybe something that's slightly different from other lazy libraries. So for example, things like Dask will always be lazy. They will always kind of defer the computation until a user explicitly says, okay, now I want to know my result. In Vaex, we've taken a little bit of a different approach where we've put an emphasis on the exploration. So more from a data science perspective, you get a new data set, you need to do a lot of trial and error, filter the data, look into it, and you want to have immediate answers to your group bys, aggregations, filters, and so on. However, when you're more set on the process, like I'm set on this demo, you can still optimize things further. For example, every operation that would be otherwise computed eagerly, we can pass this delay true argument. So for example, when we do a count, when we calculate the mean, sum, group bys, and so on, we can pass this delay argument that says, okay, we're not done specifying the list of operations that we want to do. So wait until the code meets this execute statement. At this point, all of these operations will be executed in parallel, and Vaex will try to find the optimal computational graph and how to do them in the most efficient way. So now if I execute this code cell, you see that all these operations where we use the delay true argument were done in a single pass over the data, and if we compare the timings, it's a bit more efficient. Another interesting optimization that you can do is turn on caching. So Vaex implements quite a granular caching mechanism, and it supports both disk and RAM caching. So we can turn it on globally like this, check that it's on, and now we have the very same code, nothing has changed. We run it once, we can scroll down. Yeah, nothing has changed because now it's the first time that we run this set of operations after we turn on caching. But if we run it again, we see that the results are basically taken from cache. And the fun thing or the good thing here is that the cache is done on the kind of small level of each of these operations. So for example, even though we never explicitly wanted to know the sum of this particular column, if in the future we want to do some other computation that requires the sum of this column, it will be used from cache directly. So that's kind of the power of doing this on a very granular level that Vaex provides. So at this point, we can take the outputs of our function and visualize them. So first, we know what we want to do. Let's say we're set on computing some high-level statistics like the counts, means, and group by aggregations. We can wrap them into a function. We no longer need the progress bar because we're happy with the performance. We can test it out, give it a filter, give me the results of my workflow, and then we can wrap it up in some sort of visualization. Here, I use some Plotly code to create a world map. You'll see it in a second. And then you can display these visualizations or sets of visualizations with your favorite dashboard making library or web app making library. Here I'm using Solana. It's a nice tool. You should check it out because it allows me to do this demo in the Jupyter notebook, so I don't have to switch context too much. Also works outside of Jupyter, and the app that we built will look like this. This is the output of all the group by aggregations, and this is the output of the individual counts. So for example, now I can select additional actor code, and the computations will be triggered. You will see the new definition, the map has been updated, and because we have caching on, if now we go back to the original state, things will be immediately, we can immediately go back. So that's it for the demo. Let me go back to the slides in a second. So for a bit more involved examples, you can check out these two examples that we have made with Streamlit and Dash. These are live links, streamlit.vaex.io or dash.vaex.io. The Streamlit version is essentially a slightly more sophisticated version of the web app I just showed you in Jupyter. And on the right, we have an example with Dash, with Plotly Dash that, well, you can also check out in your own time. Also, the implementation of both of these dashboards is available on our GitHub account. So please feel free to have a look and see how we implemented these things. And I think it's important to know that Vaex is used in production. We have worked together with Plotly, so it's quite tested under Flask and Fast API. And it has nice features for, well, such as the memory mapping processes where you can share data between different systems and also the integration caching. And some companies, or that we know of at least, do use Vaex in production for important applications. Most notably, Galileo, I think, has based a lot of their data processing service based on Vaex. So if you do want to learn more about that, please get in touch with us or with them for that matter. And finally, we do run a consultancy around Vaex. That's how we are able to continue development and maintaining the project. So you do get in touch if you're interested. Or in general, you can get in touch with us through the main channels, GitHub, Twitter, and so on. Please get in touch if you have any questions or issues or ideas or feature requests. We love to hear from everyone, and hopefully we can do more work together to help on our own data journeys. So thanks.
Thank you very much, Jovan, for the amazing session. And I can see there are a few questions on the comment section. So one of the users is asking how they can access the notebook you've just shared.
Yes, so after this talk, I'm going to put all the materials, so the notebook and the slides, on a GitHub repo called Vaex Talks, and we'll share the link in Discord as soon as that's live. I just wanted to have the real version of the notebook from the talk to be in GitHub. That's why I didn't post it before.
All right. Thank you very much. And the next question from Mikhail: what's Vaex performance for small dataset comparable to Panda, slow, faster?
So the question is how small. If they're very small, like 1,000 rows or 10,000 rows, it will depend a bit. So if you have a super powerful machines with many cores, there will be some overhead in Vaex due to parallelization. So it could end up being slower. But if you, I think, surpass a few 100,000 rows, it will be the same.
All right, thank you very much. And the last question from Joseph. So with caching, is there time period before Vax reruns an operation to get metrics like sums, etc. to keep the value current?
Yes, good question. So there are several strategies of how of how the caching works. So you can limit memory. I think you can also limit by time. This does deserve a better documentation from our side, but there are several strategies on how you can keep how long you keep the cache and when you decide to recompute. Maybe I can get back to this in Discord, and maybe Maarten has already answered this in Discord. But yeah, there are several strategies to do this.
All right. I think Martin also put on the chat that no, it will use LRU cache as well.